Good afternoon, welcome. I hope you guys have been having a good day, at least a decent day, and that you had a good weekend, that you are relaxed and rested. Hopefully yesterday was good. Today we're going to be doing section 7.1 and 7.2 and 7.3 in our lesson today, which is sample proportions and sample means. We're doing them together because they're very closely related. And they kind of work, they're dealing with the same context as far as sampling distributions. So we're going to do sample proportions first, do an example, sample means, do an example, and then we'll be done. Shouldn't be too bad. Yeah, there's a good amount of information that's going to come at you today. There's going to be a few points where I'm going to say you should write this down in your notes. That's when you should really write those things down in your notes. Some of the other things are just there to help make sense and to help move us towards the thing that should be in your notes. So please keep that in mind as we move along. So with that, we're going to get started. And as usual, if you have questions, if you need me to slow down, you need me to repeat something, you need to write something down, please let me know, raise your hand, shout at me, type in the chat. One of those things works. All right, so there's that, that one. All right, so here we are, 7.2 and 7.3, sample proportions and sample means. And we are in chapter 7 of sampling distributions. So our objectives today, we want to find the mean and standard deviation of the sampling distribution of a sample proportion or sample mean. We're going to check the 10% condition before calculating the standard deviation of the sample proportions or sample means. Right, we have to check that the sample is not more than 10% of our population that we're sampling from for both types of sample distributions. We're going to determine if the sampling distribution of sample proportions is approximately normal. We're going to explain how the shape of the sampling distribution of a sample mean is affected by the shape of the population distribution and the sample size. And if appropriate, we're going to use a normal distribution to calculate probabilities involving sample proportion or sample mean. So that's the goal for today. And we're going to start with our sample proportions. All right, so we're going to look at the sampling distribution of p hat. So the main question we want to ask is, how good is the statistic p hat as an estimate of the parameter p? Sampling distribution of p hat answers this question. We're going to consider the approximate sampling distributions generated by a simulation in which SRSs of Reese's Pieces are drawn from a population whose proportion of orange candies is either 0.45 or 0.15. We're going to consider what we notice about the shape, center, and spread of these distributions. So first, we have the distribution of our orange candies from a population whose proportion of orange candies is 0.45. Right. And one of the samples, one of our samples of 25 candies, resulted in a proportion of 0.48. The sample distribution after doing 400 samples, we get a center that's essentially at 0.45, which is good. It's meaning that this is an unbiased statistic. If we increase the sample size to 50, excuse me. No, never mind. If we increase the sample size to 50, right, then we see that we get a similar distribution, right? We still have the center around 0.45. It is less varied, right? It's a little more narrow. And our p hat for this sample that we have pictured here is at 0.46. Right, so it's getting a little more accurate. And this goes along with what we saw in section 7.1 about the larger sample size creating less variability. If we then take a look at the sampling distributions for a population who has a proportion of 0.15 orange candies, right? Same sample sizes, 25 and 50, right? We get, again, sampling distributions that are centered at the population proportion of 0.15. They're also appearing to be relatively normal, or approximately normal. And as we do a larger sample size, we have less variation. So this tells us things. One, the shape. In some cases, the sampling distribution of p hat can be approximated by a normal curve. This makes sense because they looked approximately normal. This seems to depend on both the sample size n and the population proportion. Right, so the shape of this curve depends on the sample size, right? Larger sample, more normal, more narrow, right? And the population proportion, right? We change the population proportion, we change the center, we change the location, right? Center, the mean of the distribution is mu of p hat, and that equals p. This makes sense because the sample proportion p hat is an unbiased estimator of p. So this is kind of nice. The mean of our sample proportion is just the proportion from the population that it's supposed to be. The spread for a specific value of p, standard deviation, sigma of p hat, gets smaller as n gets larger, as it should. The value of sigma p hat, right, standard deviation of p hat, depends on both n and p. Right? So the standard deviation changes as the population proportion changes and the sample size changes. There's an important connection between the sample proportion p hat and the number of successes x in the sample. So now we're kind of referring back to our random variables from chapter 6, right, where p hat equals, right, the proportion of orange candies, so to say, equals the count of successes, or the count of orange candies in the sample, divided by the sample size, which would then be the random variable x divided by n. You do not need to write this formula down. This is moving us towards what we actually want. So again, in chapter 6, we learned that the mean and standard deviation of a binomial random variable x, this is why we brought up the random variable on the previous slide, can be found with the mean of x is n times p, sample size times proportion of the population. The standard deviation of our random variable x is equal to the square root of the sample size times the proportion in the population times a failure, right? The proportion of failures. Since p hat equals x divided by n, which equals 1 over n times x, we are just multiplying the random variable x by a constant 1 over n to get the random variable p hat. It's a linear transformation. So therefore, the mean of p hat equals 1 over n times np, right, which we're pulling from here, which equals p. So p is an unbiased estimator of, p hat is an unbiased estimator of p. The standard deviation is equal to 1 over n times standard deviation of x, square root of np times 1 minus p, which equals square root of np times 1 minus p over n squared, which equals the square root of p times n times 1 minus p over n. So the proportion of success times proportion of failure divided by n. Take square root. That's the standard deviation. We get, as a sample size increases, the spread decreases. This goes along with what we learned in section 7.1, larger sample size, less variation. And that leads us to these rules. Sampling distribution of a sample proportion. If we choose an SRS of size n from a population of size capital N with proportion p of success, we let p hat be the sample proportion of successes. Then the mean of the sampling distribution of p hat is p, just is the same. We don't have to do a calculation. The mean of the sampling distribution is whatever the proportion was supposed to be from the population. Oh, shit. Not what I wanted to press. The standard deviation of the sampling distribution of p hat is sigma of p hat equals square root of p times 1 minus p divided by n. as long as the 10% condition is satisfied, meaning that our sample size is less than or equal to 10% of the entire population we're sampling. If the 10% condition is not satisfied, then we cannot calculate a standard deviation for that sampling distribution, and it is not normal. We can't really continue and do other calculations. As n increases, the sampling distribution becomes approximately normal. Before you perform normal calculations, we need to check that the normal condition is satisfied, otherwise known as the large counts condition, which means there are greater than or equal to 10 successes, n times p, and greater than or equal to 10 failures, the other thing you weren't tracking, right? N times 1 minus p. All right, so if we want to do calculations using normal approximations, we have to check the large counts condition. If we want to calculate the standard deviation of a sample proportion, we have to check the 10% condition. Okay, so this needs to be in your notes. Okay. Can you raise your hand if you need a moment to write anything down? So now we're going to look at an example using sample proportions. So here's our example. We have about 75% of young adult internet users ages 18 to 29 watch online videos. We're going to suppose that a sample survey contacts an SRS of 1,000 young adult internet users and calculates the proportion p hat in this sample who watch online videos. Before we do any calculation, we want to identify the numbers and things that were provided in the context. So we have 75% of young adult internet users. Right. That is the proportion from the population, so that becomes P. All right. And then we have a sample survey that contacts an SRS of 1,000 young adults. That is the sample size N. And we're not provided any other numbers, right? P hat is the proportion in this sample who watch online videos. So question number 1 says, what is the mean and standard deviation of the sampling distribution P hat? So we'll do that first. The first part, what's the mean? That's kind of the easier part. The mean of P hat is equal to the mean, which is equal to 75% as a decimal, 0.75. Right? So that one's done. No calculation. We have the mean. Now, we also want to find the standard deviation, but remember, we have to check the 10% condition before finding the standard deviation of the sampling distribution of P hat. In this case, right, there's not really a calculation. We don't know how many young adults there are between ages of 18 to 29, But we can pretty much guarantee that 1,000 is not 10% of that, or it's not more than 10%. So we can simply say, since 1,000 is less than 10% of the population of young adults, ages 18 to 29, then standard deviation of p hat is equal to square root of p times 1 minus p divided by n, which is equal to 0.75 times 0.25 divided by 1,000. And we get 0.0137. As the standard deviation. And we're done. All right, so the step, right, of checking the 10% condition, right? This condition must be checked. You have to state something about it. You can't just find the standard deviation and be, okay, cool, we're done. You have to justify the 10% condition in some way with either a calculation or just by saying it's kind of obvious that this is less than 10%. All right. So we have our numbers now. Any questions about how I did these first two calculations? So then next we want to check the large counts condition. Because if that is satisfied, then p hat is approximately normal. The sampling distribution p hat is approximately normal, which would allow us to do calculations with a normal distribution if we needed to. So to check that, we have to see if NP is greater than or equal to 10, and n times 1 minus p is also greater than or equal to 10. Well, n times p is 1,000 times 0.75, and that equals 750, which is greater than 10. So that one works. Then we get 1,000 times 0.25. That equals 250, which is greater than 10. So that works. So, right, the large counts condition is satisfied. So the sampling distribution of p hat, sorry, that's really bad p, is approximately normal. And we've answered question number 2. It's important that you say the sampling distribution of p hat is approximately normal and not that p hat is approximately normal, because p hat is just a single value from one sample. The distribution of these values is approximately normal. And so then our last question is, if the sample size were 9,000 instead of 1,000, how would this change the sampling distribution of p hat, sorry. All right. So this will have no effect on the shape, so we're still going to be approximately normal. All right. It will also have no effect on the mean. Right? The mean is only affected by the proportion from our population, right? The original parameter p. It's not affected by the sample size. So we can essentially say the sampling distribution of P will remain approximately normal with mean P hat equaling 0.75. However, the standard deviation will decrease. This makes sense. Larger sample size means smaller variance, which means smaller standard deviation. And this will decrease by a factor of 3. And this is because 9,000 is 9 times larger than 1,000, the square root of 9, because we're using a square root in our calculation of standard deviation. Square root of 9 is 3. And that's where we got that number from. All right. And so we calculate our standard deviation of P hat. And that is equal to 0.75 times 0.25 divided by 9,000. And that gets us 0.0046 approximately as our new standard deviation. Sorry, it's a bad zero. Better. Is there anything I can clarify about these calculations or the things that we've done with this problem? Does anyone need a moment to write anything down from this problem? So then, I'm going to jump back into our presentation. And talk about sample means. So we're moving to the section 7.3 now at this point. So when we record quantitative variables, we're interested in other statistics such as the median or mean or standard deviation. Sample means are among the most common statistics. Consider the mean household earnings for samples of size 100. Compare the population distribution on the left with the sampling distribution on the right. What do we notice about the shape, center, and spread of each? Well, our household earnings of the population, the distribution over here on the left is skewed to the right. It has a center maybe around 0.7 or like 75 or 80,000. Doesn't get very high. Right, we're pretty spread out. Our sampling distribution, however, that is just tracking the mean of samples of size 100 is also centered at about 75 or 80,000, much less varied, ranging from like 50 to 100,000 almost is what it looks like. Much more normal and much taller. Right? But because both these histograms use the same scales, we can compare them very easily. Right? So the sampling distribution kind of takes all the data and summarizes it into what we can kind of expect the mean of our population to have, right? But it's easier to work with now because it's normal. We can do a lot more stuff with it. Right? which gives us some usable results. When we choose many SRSs from a population, the sampling distribution of the sample mean is centered at the population mean mu and is less spread out than the population distribution, which is what we saw in the previous graphics. The sampling distribution of a sample mean. This is something you're going to want to have in your notes. Suppose that X bar is the mean of an SRS of size n drawn from a large population with mean mu, standard deviation sigma. Then the mean of the sampling distribution of X bar is mu. So again, there's no calculation to do here. The mean of the sample mean, right, the mean of the sample means is the mean from the population. The standard deviation of the sampling distribution of X is the standard deviation of our population divided by the square root of the sample size. Okay, so as long as the 10% condition is satisfied, n is, which means, right, 10% condition, we're sampling less than 10% of our population. We can't do more than 10%, otherwise we can't calculate standard deviation and things fall apart. Note, these facts about the mean and standard deviation of X bar are true no matter what shape the population distribution has, whether it's normal or skewed or some other craziness, these things work. Right? The mean of the sampling distribution will be equal to the mean of population. Standard deviation of the sampling distribution will be the standard deviation of the population divided by the square root of the sample size. Does anyone need a moment to write anything down from this screen? So then sampling from a normal population. And we've described the mean and standard deviation of the sampling distribution of the sample mean X bar, but not its shape. It's because the shape of the distribution of X bar depends on the shape of the population distribution. In one important case, there is a simple relationship between the two distributions. If the population distribution is normal, then so is the sampling distribution of X bar. This is true no matter what the sample size is. So even if I'm doing sample sizes of 5, our sampling distribution will be approximately normal if the parent population was approximately normal. This is not always the case if the parent population is not normal. Okay. So we get this kind of general idea here for sampling distribution of a sample mean from a normal population. Suppose that a population is normally distributed with mean mu and standard deviation sigma. then the sampling distribution of x bar has the normal distribution with mean mu and standard deviation of sigma divided by the square root of n, provided that the 10% condition is met. So again, can't do the standard deviation if the 10% condition is not met. Does anyone need a moment to write this down for your notes? So then we're going to look at an example. All right, so here we are. We have the length of human pregnancies from conception to birth varies according to a distribution that is approximately normal. Okay, so our parent population is approximately normal, with mean 266 days and standard deviation 16 days. Suppose we chose an SRS of 6 pregnant women. We're going to let x bar equal the mean pregnancy length for the sample. So once again, before I jump into any of the calculations or any part of the problems here, let's identify the information we have. All right, the parent population is normal. That's important. Okay. There is a mean of 266. That's the population mean, mu, and a standard deviation of 16. Right? That is the parent population standard deviation. We're taking an SRS of 6. Right? The 6 is n, that's our sample size. And then we have our random variable, or not a random variable, our x bar, which will represent the sample mean. Now we can do some calculations. So question number 1, what is the mean and standard deviation of the sampling distribution of x? This is going to play out very similar to what we did in the previous example. So we get the mean of x bar is equal to the mean is equal to 266 days. Doesn't change. We just get to pull that number from the population mean. Right? And then, very much like last time, since 6 pregnant women is less than 10% of all pregnant women, and the standard deviation of the sampling distribution of x bar is sigma x bar equals sigma divided by the square root of n, which is 16 divided by the square root of 6, which gets us 6.532 days. So we have our mean and standard deviation. So now we can describe essentially the normal distribution of the sampling distribution of x. Right, it has a mean of 266 and a standard deviation of 6.532 days. So that leads us to question number 2. Right, we need to find the probability that the mean pregnancy length for the women in the sample exceeds 270 days. Right, we already know that our sampling distribution is normal, approximately normal, because the parent population was approximately normal. So we're going to do this calculation using normal approximations, right? So that means we're calculating the probability that x bar is greater than 270. So the first thing we have to do is standardize 270. So we get z equals 270 minus the mean of 266 divided by the standard deviation of 6.532. And we get a z-score of 0.61. We then go to table A, because table A is our friend. Right? We find 0.6 in the left-hand column and 0.01 across the top. That meets here at 0.7291. Right? Now remember, that 0.7291 goes along with the probability that z is less than or equal to 0.61. Right? Where did that go? 291. That's not what I'm looking for, right? This here is equal to the probability that z is greater than 0.61. So I need to use the complement rule to say that this is equal to the probability of 1 minus the probability of z being less than or equal to 0.61. Which is equal to 1 minus 0.7291. And that's equal to approximately 0.2709. And this is the probability that the mean pregnancy length for the women in the sample exceeds 270 days, about 27%. So you wouldn't have any questions about how I used the normal approximation in table A to find this answer? All right, so jump back to our presentation. And now we're going to talk about the central limit theorem. And the reason this comes up is because it allows us to deal with non-normal parent distributions. So the most population distributions are not normal. So what is the shape of a sampling distribution of sample means when the population distribution isn't normal? Well, luckily, there's a remarkable fact that as the sample size increases, the distribution of sample means changes its shape. It looks less like that of the population and more like a normal distribution. When the sample is large enough, the distribution of sample means is very close to normal, no matter what shape the population distribution has, as long as the population has a finite standard deviation. And that just means that we know what the standard deviation is. So if we draw an SRS of size n from any population with mean mu and finite standard deviation sigma, the central limit theorem, CLT, says that when n is large, the sampling distribution of the sample mean x bar is approximately normal. We'll define what large is for this course next. But this is a good thing. Right? Again, this is why I keep saying we need to know how to do normal calculations and use table A, standardized scores. It's not going anywhere. We kind of try to make everything normal if we can because we know how to work with it. All right. Does anyone need a moment to write anything down from this slide? So even when the population distribution is very non-normal, the sampling distribution of the sample mean often looks approximately normal, with sample sizes as small as n equals 25. So even if we have a small sample size of 25, we're getting close to approximately normal. We get this as kind of our rule here. So the normal large condition for sample means. If the population distribution is normal, then so is the sampling distribution of x bar. This is true no matter what the sample size n is. If the population distribution is not normal, the central limit theorem tells us that the sampling distribution of x bar will be approximately normal in most cases if n is greater than or equal to 30. So the sample size being greater than or equal to 30 is our large enough demarcation. Okay. The central limit theorem allows us to use normal probability calculations to answer questions about sample means from many observations, even when the population distribution is not normal. This is, again, very important. We like normal distributions. So with sample means, if it starts normal from the parent population, sampling distribution is normal. If it doesn't start normal, then we just need a large enough sample, right? Sample sizes to have the sampling distribution be normal. Okay. So that's good news. Does anyone need a moment to write anything down from this screen? So then to kind of put this in a quick synopsis, for sample proportions, the mean of the P of P hat, the sample proportion P, is equal to the parameter P, whatever the proportion was from the population. Standard deviation, as long as the 10% condition is satisfied, of P hat is the square root of P times 1 minus P over N, where N is the sample size. Then as N increases, the sampling distribution becomes approximately normal. The large counts condition must be satisfied to do normal calculations. The large counts condition is the condition that there is at least 10 successes, n times p is greater than or equal to 10, and at least 10 failures, n times 1 minus p is greater than or equal to 10. For sample means, the mean of the sample proportion is the mean of the population. Standard deviation, as long as the 10% condition is satisfied, of the sample mean, the sampling means, is the standard deviation divided by the square root of n. N is again the sample size. If the population distribution is normal, then so is the sampling distribution of x bar. The central limit theorem says that when n is large, greater than or equal to 30, sampling distribution of the sample mean x bar is approximately normal. So we've got conditions on both sampling distributions, sample proportions or sample means, that allow us to treat it like a normal distribution as long as certain things are met. Right. So this kind of puts them side by side comparison. Right. Does anybody need a moment to write anything down from this screen? All right. So the lesson summary. Right. We now know how to find the mean and standard deviation of a sampling distribution of sample proportions or sample means. And we know that we need to check the 10% condition before calculating standard deviation for either of these. We can determine if the sampling distribution of sample proportions is approximately normal. Right? We check to make sure the large counts condition has been satisfied. There are more than 10 successes and more than 10 failures, at least 10, sorry. We can explain how the shape of the sampling distribution of the sample mean is affected by the shape of the population distribution and the sample size, right? This means if the parent population is normal, so is the sampling distribution of the sample mean. If the parent population is not normal, then if we have a large enough sample size, more than or at least 30, then we can treat this as normal. If appropriate, use normal distribution to calculate probabilities involving sample proportion or sample mean. And that's what we looked at today. Does anyone want to look back at any of the previous slides or the examples before I close this window? Or have any questions? So then that is section 7.2 and 7.3, which basically ends chapter 7 for the most part. We will do practice activity tomorrow, going over what we just learned about sample proportions and sample means and sampling distributions. So we'll have an opportunity to practice these concepts tomorrow. As usual, I heavily encourage you to do the practice problems in Canvas for section 7, well, all the sections in chapter 7, 1, 2, and 3. And let me know if you have any questions. I should have the answers to those posted later this week. And other than that, I really do hope you guys have a great day. If you have any other questions or you need help with anything else, please feel free to stick around on this call or let me know at some other point in time. Other than that, I will see you tomorrow and have a lovely rest of your day.